Your phone is holding a secret. Inside it right now are billions of transistors, each one smaller than a strand of your DNA. For 60 years, we've made them smaller, faster, and more powerful. Moore's Law, the most reliable trend in human technological history. But something is wrong. We are reaching the end of silicon. Physics is saying no further. The atoms won't cooperate, the electrons won't behave, and the data we're generating, 120 zettabytes per year and climbing, is about to overwhelm every storage system we have. So, scientists are doing something radical. They're turning to chemistry. And what they're building is called infochemistry. Infochemistry is the science of using molecules, actual chemistry, to store information. Not electrons on silicon, molecules, chemical reactions, the same stuff your cells use to run the most sophisticated information processing system ever evolved, life. The word itself has an interesting history. Originally, infochemicals were communication molecules, pheromones, the chemical signals bacteria use to coordinate behavior, nature's original data packets. But George Whitesides redefined the term. He saw molecules not just as passive actors in chemical reactions, but as potential computational units, things that could take inputs, process them, and produce outputs. The molecule as a machine. And that insight launched a scientific revolution. Today, infochemistry has three pillars: molecular logic gates, molecular data storage, and smart materials. Let's go through each one. Every computer that has ever existed runs on logic gates. These are the simplest possible decision-making devices. An AND gate says, I'll give you an output only if both inputs are present. An OR gate says, I'll fire if either input is there. A NOT gate flips the signal. Chain millions of these together and you get computation. Your entire digital world emerges from these three ideas. Now, what if instead of electrons on silicon, you built those gates from molecules? Here's how a molecular AND gate works. Take a fluorescent molecule, one that can glow. Define its glowing state as binary 1 and its dark state as binary 0. Now, expose it to two chemical inputs, a specific pH level and a calcium ion. The molecule is engineered so that it only glows when both inputs are present simultaneously. If one is missing, it stays dark. That's computation, performed entirely by chemistry. No electricity required. DNA logic gates are even elegant. DNA has a beautiful computational property. It follows strict pairing rules. Adenine always bonds with thymine. Guanine always bonds with cytosine. Scientists have learned to write logic circuits in these rules. A specific DNA strand, designed with particular sequence, acts as an input. Another strand acts as a gate. When the right input strand binds, it triggers a cascade, a molecular cascade that ultimately produces an output signal. And these gates can be cascaded. The output of one molecular logic gate becomes the input of the next. Sound familiar? That's exactly how your CPU works. Now for the most mind-bending part of infochemistry. DNA data storage. Let's start with a number. 400 exabytes per gram. That is the theoretical maximum information density of DNA. 1 gram, smaller than a paperclip, could store more data than the entire current global digital archive. Not 10 times more, not 100 times more, millions times more. How is that possible? DNA has 4 chemical letters, A, T, G, and C. Assign binary values to them, say A and T represent 0, G and C represent 1, and suddenly you have an information encoding system. To write data, you synthesize a DNA strand with the corresponding sequence. To read it, you sequence the strand. The process is slow by silicon standards, but the density is unprecedented. In 2012, the Weiss Institute at Harvard encoded a 52,000-word book into DNA. By 2019, researchers had written 16 gigabytes, the entire English Wikipedia, into a vial of synthetic DNA you could hold in your hand. And in February 2025, a team published in Nature Communications what they called a molecular hard disk, Using self-assembled molecules, just 200 of them in a monolayer, they achieved 96-state memory performance. That means each molecular unit can store 6 bits of data. The power consumption? In the picowatt range. That's a trillionth of a watt. Your phone uses 1 billion times more power for the same operation. And this molecular hard disk also performed in situ encryption, processing and protecting your data using the same molecular system that stores it. The third pillar of infochemistry is smart materials, and this one you can almost touch. Smart materials are substances engineered at the molecular level to detect information about their environment and respond to it, not by sending a signal to a processor somewhere, by responding directly. The material itself is the computer. Think about what that means. A material that knows its environment and acts on it without a chip, without electricity, without code. At ITMO University's Infochemistry Center in St. Petersburg, researchers built a breakthrough: pH-responsive multilayer coatings on implantable surfaces. These coatings detect acidity in their immediate environment. Here's why that matters medically. Tumors are acidic. Healthy tissue is not. A polymer capsule that holds a drug and releases it only when it detects an acidic environment can deliver chemotherapy directly to cancer cells. It doesn't need GPS, it doesn't need a radio signal. The chemistry is the intelligence. And then there's one of the most beautiful phenomena in all of chemistry: Liesegang ring formation. When certain chemical reactions occur in a gel, they spontaneously self-organize into perfect concentric rings. Scientists at ITMO have embedded silver nanoparticles in these rings, creating self-assembling molecular barcodes. These aren't printed on the material. They grow from the chemistry, and they can be read optically. No power, no battery, no chip, to authenticate products, drugs, documents, even currency. And finally, nanorobots. This is where infochemistry starts to feel like science fiction. In 2017, a team at Caltech designed a DNA nanorobot, a folded DNA structure about the size of a protein that could walk across a flat DNA origami surface, pick up cargo molecules, and sort them into defined locations. It had legs, it had an arm, it had programmed behavior, and it ran entirely on chemical energy. No battery, no external control signal. It was a programmable machine built entirely from chemistry, at a scale 10,000 times smaller than a human hair. So where does all this lead? Imagine a future where you swallow a therapeutic, not a pill, but a collection of molecular logic machines. They enter your bloodstream, they navigate to a tumor, they perform a chemical computation. Is this a cancer cell? If both oncogene markers are present, and gate fires, they release the drug. If the markers don't match, nothing happens. Precision medicine at the cellular level. No side effects on healthy tissue, no collateral damage. This is not science fiction. This is the published roadmap of infochemistry research. Environmental monitoring could be transformed. Molecular logic sensors dispersed into water systems detecting heavy metals at parts per trillion sensitivity. Already, researchers have built molecular AND gates that detect cadmium in rice samples, a real-world contamination problem. Scaling those systems up means self-monitoring rivers, smart soil, infrastructure that alerts authorities to contamination before humans can even detect it. But let's be honest about where we are. Molecular computers exist today only as laboratory demonstrations. They operate at room temperature, which is good, but they're slower than silicon by orders of magnitude. Error rates in DNA logic can be significant. Manufacturing self-assembled molecular systems at commercial scale remains a profound engineering challenge, and the interface between the molecular world and our macro-scale digital infrastructure, that's still mostly unsolved. These are real obstacles, but they were also the obstacles of transistor development in 1960. The first transistor in 1947 was a fragile, clunky, room temperature curiosity. By 2007, we had 1 billion of them in your pocket. The trajectory of transistor miniaturization took 60 years. Molecular computing has been seriously pursued for only 30. And the pace of discovery, 2021 papers on DNA logic circuits, 2025 papers in Nature Communications on molecular hard disks, is accelerating. The time constant is compressing. The molecules are ready. The science is ready. The question is whether our manufacturing and engineering capabilities will catch up in time to meet the data tsunami that's coming. Infochemistry is not a fringe idea. It's a peer-reviewed, globally funded, Nobel Prize-adjacent field of science with real results and a clear direction. ITMO University, Harvard, MIT, AGH University in Poland, major institutions have staked their research futures on this, and the vision at the center of it is simple and profound. Matter that thinks, materials that compute, chemistry that stores. Not as a metaphor, literally. We built the digital world on sand, on silicon refined from sand. The next world might be built on the molecules that are inside every living thing on Earth. If this episode opened your mind to something you didn't know existed, that's exactly what Cipher Sci is here for. Drop a comment. What application blew your mind the most? Hit subscribe. There's so much more coming. Next time, quantum biology. How life might already be using quantum mechanics to navigate, to photosynthesize, maybe even to think. I'll see you there.